So, as you might have noticed, this workshop is about the connection between graph theory and quantum information theory. And when Robert asked us to submit the abstracts, the titles of our abstracts for our talks, out of a lack of imagination, I just quickly submitted the title Tales from Graphland. So this is Graphland, and these are the tales, or two instances of such a connection between graph theory and quantum information theory that we've been thinking about recently. On the one hand is to further push the idea of generalized graph states, so universal resources for measurement-based quantum computation, and to what could be conceived like the computational power of quantum wires. So that's measurement-based quantum computing beyond forwards one-way model. On the other hand, this is the connection that Aaron has already mentioned on expander graphs and quantum expanders, so particular pseudo-randomizing, completely positive maps acting on quantum states. But anyway, 50 minutes are not a lot of time, and when I put my slides together last Sunday, the second subject was kind of slowly melting away like ice in the sun, and admittedly, I will this talk primarily be concerned with like generalized graph states, so new results on new models for measurement-based quantum computing, and really only if there's this time, there will be a kind of short teaser on the second subject. So I'm aware that there are some people in the audience who, either by David or myself, heard a talk on this research direction, so try to be patient. Today, it shall be about a more systematic approach to finding such new models for measurement-based quantum computation beyond the one-way model. Okay, anyway, let's start at square one. So Dan has very nicely explained yesterday what a graph state is, associated with any simple undirected graph, and that, well, we can associate the vertices with qubits, prepare the state in the superposition of all binary words, and then apply a phase gate between any two qubits, any vertices that have an edge in the graph. So these are stabilizer states, these graph states, and they have a number of interesting properties. And one of the interesting ones being that they can be universal resources for measurement-based quantum computation. So if we do local measurements on a cluster state, they're just as powerful as the circuit model for quantum computation, in that we can encode the input by suitable measurements on a cluster state. Then we can simulate any quantum circuit by sophisticated measurements and read out at the end of the day only by doing local measurements on like a family of particular graph states or cluster states becoming larger and larger. So graph states can be universal resources for quantum measurement-based quantum computing. But sure, we all know this. This is part of the point of this, that we are here. So the question that we asked last year, that kind of started this program that we have in mind here, was the simple question, well, very nice. This is a beautiful result, in particular since we get away with unitary control on the way. But, well, what if we just do not have a graph state, but say some other state that has very different correlation or entanglement properties, just some state, will that have computational power? Can we do computing with it? So can we find new models for measurement-based quantum computing? And can we find new resource states for measurement-based quantum computing beyond graph states or beyond cluster states in the first case? And well, that such a, the motivation from a physics perspective of such a program is quite obvious. Clearly, you can think of many different meaningful preparation mechanisms in a physical architecture, and it's by no means clear that the cluster state plays any special role in the preparation of such a quantum many-body state to be a resource for measurement-based computing. Or one could even push it further and think of like tailoring a state or a computational model to a state that you anyway have in the lab, or at least could conceive of having in the lab, kind of reverse engineer and kind of think of tuning the computational model to the state that you have at hand. Or it would be a desirable property to be like protected via a gap in the gap model. If you have a local Hamiltonian of a gap model, to be gapped, to be protected from excitations similar to the way in topological quantum computing, such that we are always in the ground state and don't get excitations on the way. Then from the computer science perspective, to be simuleerbar on the one hand, and to be a universal resource on the other hand, seem to be complementary concepts. And to be classically efficiently simuleerbar is related to, say, the computational complexity of tensor contractions. And we've seen and will see how this is also related to getting partition functions in quantum statistical models. So to see where the boundary is between like being classically efficiently simulatable and being a universal resource for quantum computing, to kind of delineate this boundary or to identify this boundary seems a quite promising enterprise. So just to remind you, say graph states have a number of interesting and useful, but also quite special properties among quantum many-body states. For example, they have a lot of entanglement. So if you pick out a site, then this will be maximally entangled with the rest of the chain, with the rest of the system. So this guy will be maximally mixed as a reduced state. And clearly, most many-body states will not have that property. Or you have no long-range correlations whatsoever in the graph state, which is no accident, because if you think that this measurement here is correlated with any other measurement somewhere in the lattice, if everybody is correlated with everybody, it seems impossible to conceive that you could think of a computational model, because your quantum information diffuses to wherever in the lattice all the time, and you cannot really think of confining your quantum information to a specific region within the lattice. So that seems to be an obstacle of finding models of computation. And there are a number of other properties of that sort that show that graph states have a number of interesting and desirable properties, but they are extreme and very rare among quantum many-body states, for example, ground states of gapped models or states that are preparable via other quantum cellular automata or so on. So what states are universal for measurement-based quantum computing? And obviously, we know that, well, obviously cluster states or families of graph states are known to be universal resources for quantum computation. And that's the point of the nice work of Hans and Robert some years back, to show that the one-way computer can just simulate any circuit model of quantum computation. Then interestingly, there was a lot of work following on this specific one-way model for quantum computation. There was work on the computational model, of understanding the role of entanglement there, and to kind of generalize it to higher dimensional constituents, or to relate it, like as Debbie did, to other instances of measurement-based models. But it seems also fair to say there was very little progress on entirely new models altogether, or just different resource states different from graph states. And so last year we came from a kind of different direction, as we will see, from a kind of approach of matrix product states and higher dimension analogues, to kind of see that, well, strangely, the graph states are by no means so special among like many-body states, and that there are other resource states that also allow for universal computation based on measurements. And in fact, there's quite a zoo of computational models and of states that give rise to universal models. So we were quite excited about that. And that's kind of started a kind of more systematic program of trying to understand more systematically what's going on here, to kind of classify what resources do the job and what don't, and kind of get a more systematic picture or a toolbox of finding such models in the first place. So this is the agenda today, to kind of give a few examples. I mean, that will be very superficial, of course, given that there's not so much time, of some steps towards a systematic toolbox of constructing such new models, and only if there's time, some teaser on other things. Okay, so what's the language that we have here in mind? So we have, say, a lattice, some graph, for example, a two-dimensional cubic lattice, a ground state of a gap model in a two-dimensional lattice that's just structureless. But of course, we're totally free to put in structure by the measurements that we perform, so we can single out things by our measurement pattern. So we could think of like pinching out some of the systems along the way, and similar to the one-way computer, think of like horizontal wires as being encodings of our logical qubits, whereas certain bridges serve as, well, kind of the role of quantum gates between these wires along the way. So we can think of a kind of measurement-based analog of a qubit in such a fashion on a lattice in terms of wires and gates. So in this way, we can think of simulating the circuit model, but the tricky bit is that the correspondence between the logical information and the physical qubits is very much non-one-to-one. So we will see that the logical qubits can be very spread out in certain correlations in the lattice. So that's very much non-one-to-one, but you can nevertheless think of like wires and putting things together, similar to a quantum circuit, but based on measurements. So we will see. So this, as such, is very vague. We will see quite precisely what this means. So let's look at the language in just a one-dimensional shape, just a one-dimensional, well, what you could call a quantum line. And at first, it seems that we are in a pretty damn dilemma here, because but we need to keep track of local measurements and have a language of what happens if we do something locally. But then, on the other hand, we can never talk about the whole lattice efficiently classically, because if we could, then we would not do quantum computation, and we would be screwed. So we have to find a right way of talking about such quantum many-body states, and kind of a new input here, a kind of tool that's very useful in this context, is provided by what is called matrix product states or penta product states, PEPs, or high-dimensional analogs, so tools from many-body physics. And condensed matter people are very familiar with these objects because these are the ones that are generated by DMRG, so density matrix renormalization group approach. That's a method of numerically simulating ground states of quantum many-body systems as a variational principle. But here, we're not concerned with classically simulating properties of quantum systems, but with kind of trying to cook up computational models for quantum computing in the first place. But you will see that a very similar language gives rise to exactly the type of objects that we have in mind. So the ingredients that we need are the following. So we have our one-dimensional spin chain, and now we glue stuff to the spin chain in our head. I mean, it's just a mathematical abstraction. So we think of a substructure, a d-dimensional substructure, where d is some dimension that can be larger than the physical dimension, very large, 10,000, whatever, and we call this correlation space. Then we associate with each site two matrices, two d by d matrices.
The CD is on each of the sites. I just wasn't clear earlier. Now I think it's clear now, given that you were talking about matrices on each.
Exactly. So we have associated with each of the spins matrices, but we pick them all the same, but we could pick them differently. So there's per side, there's a matrix A0 and A1 as a d by d matrix acting in this correlation space. Yeah? So and there's boundary condition vectors representing the boundary conditions, but that's not so important. So as such, it's just certain matrices equipped with the signs. Now, this is the state vector of a matrix product state. So here is that's the computational basis element, so a binary word. And here we have a product of these matrices. And which product, well, it depends matrix product state, and which product we have depends on the binary word we have on the left-hand side. Well, that's certainly a meaningful definition of a state vector because we can write out all the coefficients, but we better, and here that's the physical state, and these are the matrices in some abstract correlation space, but that's certainly a meaningful definition of a state vector.
I'm not getting the equivalent. So C is the quantum state.
Yeah.
And S1 through Sn is a bunch of bits. Like
it's just 0, 1, 1, 1, 0, 0, 0, 1.
So and you can define, you define this inner product as the thing on the right.
Exactly.
Okay.
This is the definition. Yeah. So the question is, fill this definition with meaning. That's the task for the next 3 minutes. Yeah. So that's a definition, but we better, as you say, fill this with some intuition. Now, these are matrices. Matrices are tensors of degree 2 with 2 indices, and tensors can be represented, as you all know, by boxes with wires representing the indices of the tensor. So we pick out a site, the kth site, and this box will have an input and an output, and the input on the left-hand side will encode the input that comes from the left-hand side of the chain. So at the site, we will change the state of the correlation system, so in this d-dimensional subsystem, by applying the matrix A0 if you have spin down, and A1 if you get spin up, and that information is passed onto the right-hand side of the chain. So these matrices are used to convey non-local information and the correlations in the system that we have. So the intuition now is that we take these operators literally as really operators acting in correlation space, as really operators that do something, and we apply A0 if we do a Pauli Z measurement and get spin down, and A1 if we get a spin up in our measurement. Yeah? So, but that's not enough. That's only Z measurements of our sites in a certain basis. We need more. We need to know what's going on if we do a tilted measurement in the tilted basis. So, well, it's not difficult to see that this gives rise to a linear combination of these matrices with a suitable scalar product such that, and that's the important point of this method section, the overlap of that type, if we measure along the spin chain in certain directions, that this overlap is just given by this product of all these matrices which are linear combinations of these matrices. Yeah, it's easy to see. Just from, well, think of one side. And if you look at the expression that we had before with the overlap of 0 and 1, if you make a tilted measurement and the coefficients will be just inherited, you can flip them over to the matrix side and do that. So it's not difficult. Okay, that's a triviality, but it's nevertheless conceptually an important point that you have measurements along the side, and this gives rise to a sequence of operators as a product here. So this can be reread as a computation, but not in the physical space, but in the correlation space. Meaning, you start up with the left boundary condition as a preparation of your correlation system. Now you make the first measurement of a spin on the first spin, on the first site, proof, in some direction. Hence, you apply the matrix A of this angle on the correlation space and pass this onto the right-hand side of the next site. Then you do new measurement in some angle, and that gives a new operator. If this is unitary, it will preserve information that's passed onto the right-hand side, and until you hit the right boundary condition, and that's the probability of this sequence of measurements to occur.
The usual kind of quantum, the qubit space we're talking about, is it different?
Yeah, that's what I'm trying to say now. Because it's a good question. That's exactly the point. Yeah, so measurement is driving the computation forward, but not in the qubit space, but in this correlation space. So in a way, the measurements you do in the physical space steer what matrix you apply, but that matrix doesn't act in the physical space, but in the correlation space. So it's a kind of behind-the-scenes measurement where you measure in the physical system, and you apply the big matrices in correlation space depending on what measurement outcome.
And in the qubit space is a projective space, right? And here is the CPT.
Absolutely correct. It's indeed, yeah. So as Robert said, it's all in the correlations in the one-way computer already. So this picture enhances this view in that here we have a mathematical object of graph with the correlations. This is the correlation space, matrix product state that is responsible for the correlations here. Yeah. So, okay, that's only good enough for one-dimensional wires. If you think of higher dimensional systems, you think of general lattice defined by graphs. Then you need tensor networks with tensors of a higher vertex degree, but just of the vertex degree of the tensors. So, for example, for this two-dimensional lattice, you would have tensors of degree 4 with inputs, two outputs, and all the boundary conditions, which makes things very, very messy if you want to do something with it. And it's quite painful, but, well, conceptually, it's very similar that you do physical measurements on the sides, and you drive the computation in correlation space by making measurements on the sides. So that's kind of the framework that we have invite. And it can be done on a classical computer. And linking to Dan's talk yesterday, you need a P-side computer. So the L side computer will not be sufficient. You need a P computation sideline. You need everything. You will see. Yeah? It's impossible to see that you need a subclass of P for the type of computations you need to do, but it's all efficient. Oh, I'm much slower than I thought. Okay, so classification of computational wise. So for the two-dimensional settings, you can do a lot, and we have looked at lots of models and kind of tried to shoot down properties that you need. But in order to be more systematic, we want to see whether we could classify like one-dimensional wires that can be put together with gates to think of a systematic way of approaching the construction of such models. So as a kind of primitive to systematically build up such models, we could think of, say, states on a one-dimensional spin chain, one-dimensional guy, that allows, of course, for the transport of logical qubits along the chain, otherwise we are dead. It should be preparable, preferably with nearest neighbor gates, then translation invariant for convenience, and we should be able to couple that to a two-dimensional or higher dimensional graph resource of whatever sort. So that's our primitive, kind of our wire axioms that we would like to look at for the next few slides as a primitive to cook up systematically new models. So I have to 35, right? Okay, good. So I mean, one resource of that type we of course know that's in familiar territory, the one-dimensional cluster state, where these tensors are nothing but these elements here. And this is not in the physical space, but in the correlation space that happens to have the same dimension of a qubit space. Yeah? But the 0 is for the physical measurement, and that's living in correlation space. So if we measure in the X spaces along the chain, physically, what we do see is we get a minus outcome. That means we apply in correlation space an HX, Hadamard Z. That's just reformulation of what we know. And that's unitary and passed on to the right-hand side. Then we get a plus outcome that is a Hadamard and passed on to the right-hand side. We get a minus outcome Hadamard Z passed to the right-hand side, and we get a minus Hadamard Z passed to the right-hand side. Exactly. That's exactly the formula that's just exactly the formula that we saw earlier, indeed. Well, thanks. Yeah. So the characteristics here, what we see is we have the always-on interaction, Hadamard. That's always coming, right? We have that. Then there's a byproduct operator, Z, that we only apply if we are unlucky and get the wrong measurement outcome. What this happens, there's a byproduct. And we are unbiased with respect to having positive and negative outcome. Each is just probability 1. But there's one more characteristic, because that would be quite stupid. That would only allow us to transport along the chain. We need more, but fortunately we are lucky, and if we do any measurement in this equatorial plane, that gives rise to a Hadamard and this phase gate in correlation space, which together with the Hadamards allows us to do any local unitary and effect by any SU2 element in the chain, and hence any computation. So that's what we call freedom of choice. Yeah. So that's the interpretation of this. So you have the always-on interaction, Hadamard. So that allows for universality, because if they didn't have that, we would be stuck in the equatorial plane forever, and we could not do universal computation. So that's what we want. Then there's the byproduct operator Z, which is evil, but it's not only evil, because we kind of need that, because it's the necessary evil of entanglement, because if we trace out the rest of the system and look at the reduced state, we don't want to have a pure state, because that would mean that we have a product state to start. Then the plus and the minus being totally unbiased is the signature of maximal entanglement of the cluster. And then there's the freedom of choice that allows us to adapt to different algorithms. So this is kind of the interpretation of what's going on. But let's push that further and look at kind of general wires on the wire axioms that we looked at earlier, like on one-dimensional systems that allow us to do the things that we have there. Yes.
So, like, allow the first point there, why is Hadamard always on? Is it because early in the chain somehow is always H there, H something earlier.
Yeah, it's the way the state is defined. It happens to be a Hadamard. And in which respect it turns out that you're happy that you have the Hadamard. Because if you're happy that always on means whatever measurement outcome you get, you first apply a Hadamard to pass it on. No matter what. It's always on. Yeah, exactly. Yeah. So the axioms for computational wires. So here are the properties again. We want to have a qubit chain. That just means that the physical dimension is 2. Well, that's what a qubit means, right? So it should be preparable by nearest neighbor unitary gates, which means that the computational power, the entangling power of the gate is 1. So the correlation space is also 2-dimensional. We have 2 by 2 matrices. Then it's translation invariant, which means that we have the same, as you might ask earlier, the same matrices A0 and A1 per side, position independent. And we would like to allow for transport of a logical qubit, which means that we don't want to lose information, and there should be one basis in which we can measure such that we get a unitary transport in the correlation. So there should be some basis where these guys are up to a factor that only pops up in normalization, unitary matrix. And it should, that's of course the technical bit, to couple to a 2-dimensional resource, and that I will only sketch very briefly later. So these are the axioms for computational wires, and using the gauge freedom of matrix product states, we can write down the most general form of such computational wires, and they have a very similar structure. Yes?
So do you get back from the correlation space transformation to the qubit space transformation by looking at the A's and then inverting together?
Absolutely. You contract the tensor network. In one.
Can I just ask a question as the chair? How are you doing for time? Because perhaps we have only 20 minutes left.
Yeah.
So maybe we should stop. We'll extend it by 5 minutes, and maybe we should leave questions to the end.
No, okay. I try to be quicker. I skipped the expander anyway. So okay, you contract the tensor network. In 1D it's efficient. In 2D it's sharp p hard, right? So that's the irony. You can't keep track of what happens on a lot of measurements. You have No, it's good. It's great. Thank you. So the point is you have a. No, sorry. It's great that you ask questions because that's support for the understanding. So you have a 1-dimensional wire. You can contract the tensor network, but if you have a 2-dimensional wire, you can still make a computational model. But in order to find out what happens, you need to construct the tensor network, which is P sharp hard, which is kind of not possible, which is good because you want quantum computation. So this is the form of the most general wire. So that has a very simple form, 3 ingredients. One is the always-on interaction in the same spirit as before, W, some unitary, which is the Hadamard for the cluster. Then there's a byproduct angle, phi, taking the value pi over 2 for the cluster, and the bias parameter that takes the value pi over 4 for the cluster. It's not so difficult to see. What is a bit more difficult to see is that we are here lucky twice in a way, in that whenever we have a measurement basis such that we can do transport in a unitary fashion along the chain, then there is a full 1-parameter family of such bases, which means that we get the freedom of choice kind of for free, which we always have for wires. And these sets are closed under passing to the orthogonal measurement outcome, meaning whenever we get the wrong measurement outcome, we're not screwed, but we are still within the set. So this is a closed formulation of kind of wires along the chain. Yeah, this is just, exactly. That's just the full classification. But the interpretation of these angles is quite fun. So the byproduct angle, in a way, satisfies how much you are messed up if you get the wrong measurement outcome, whereas the bias parameter says how likely it is to get the wrong measurement outcome in the first place. So if you think of, say, the byproduct angle to be pi, then you can look at the dependence of the reduction of the reduced state on the bias parameter, and what you find is that you can have any bias between the probability up and down that can be arbitrarily close to 1, which means that the reduced states can be arbitrarily pure of your system. You can nevertheless transport and do any rotation along the wire, but locally, every guy looks arbitrarily pure as you want. That's kind of strange. So maximal entanglement is by no means necessary. Having no maximal entanglement is not an obstacle against universality in such a system. That's one way of playing it. You can also think about the byproduct operators and say take the k square root of the Pauli X operator as your always on interaction term. And what you then see, it's a wire, of course, you can transport and do any unitary thing on the way. But what you also get is long-range correlations. It's a gap model, or like in a gap model, you get exponentially decaying correlations, but everybody is correlated with everybody. But long-range correlations, because it's a wire, is not an obstacle to universality. How can that be? You have correlations. But the point is that, well, the price to pay is that you get a random length of computation, but that's the perfect price to pay, appropriate price to pay, that you need sometimes 2 measurements and sometimes 3 measurements for the same task if you can show that you have a finite number of steps to do a certain thing. So that's the non-one-to-one thing here, in that the logical qubits are very much spread out in the correlations over many, many physical sites. And by doing measurements on the sites, you can kind of steer the logical qubit that's encoded over many sites in the correlations. Yeah, so in this sense, it's very much non-one-to-one, the logical qubit and the physical qubit. And there are more games you can play once you have this classification at hand. But what I would like to emphasize also is that there are kind of also more physical examples of that sort. For example, you could take the ground state of the gapped AKLT Hamiltonian, or variant thereof, which is a gapped nearest neighbor Hamiltonian model, which gives rise to a quantum wire. So that's the ground state of a nearest Hamiltonian. You're protected by a gap, and you can nevertheless transport and do any local rotation. And I think Akimasa will also follow up on this in his talk later today or tomorrow. Or you could think of Bose-Hubbard wires. So you have like tunneling to nearest neighbors with a Bose-Hubbard Hamiltonian, and then once again, in the kind of quantum cellular automata picture, which is the setting that you would naturally have in a kind of optical lattice with an optical superlattice. And indeed, we are talking to Manuel Bloch about such things to think of wires of that sort. So that's to show that these quantum wires are not necessarily totally crazy, but they are physical, meaningful ways of preparing such wires in several fashions that are quite different in many ways from the class system. And what I sweep under the carpet, but that's of course the hard work, is that the one-dimensional wires can be glued together with appropriate switches to make like 2-dimensional wires to get graph structures of some graph. So one could think of a switch based on phase gates, or switch based on exchange interaction, or very gentle couplings that have very little entangling power, but these wires could be glued together with such gates on the way to make a full universal resource. So this is kind of a toolbox of putting things together. You can have your wires, you have your couplings, and you can think of like putting together crazy models. The limit is your imagination of thinking of one-dimensional wires, say with phase gate interactions coupled by exchange interactions and so on. And this would give rise on some graph structure to a universal model for quantum computation, possibly with very long-range interactions on very little entanglement per side and so on. So maybe at the end of this this part, I pick out a certain resource that's specifically fun. This also links to Robert's work recently. That's, you could think, you take the planar version of Catalytic code state as a universal resource for measurement-based quantum computing. You have this state, do local measurements, and you want to do universal computation in that fashion. Very nice. You could think of, say, wires that you put through. In your head, this is our logical qubits, and you would like to do sophisticated measurements to couple them together to get a universal model for computing. Well, so this is the tensor network formulation of such a state. So we have alternating layers of horizontal and vertical tensors in this tensor network description, where these horizontal and vertical tensors factor in that way, where you have z to the power of s, which is not so difficult to see. So if you do just a if you do a Pauli Z measurement here, what you do get is you just pass on information on a wire up to a correlated ZZ error. You can pass on information through the lattice. That's nice. Even more, if you do a general measurement in the YZ plane, you get, if you think of this as an input and that as an output, what you get is a gate that has entangling power. And if phi is pi over 2 or minus pi over 2, you get a gate that's locally equivalent to a C0 gate. Wow, we thought, great. Typically, it's so painful to get an entangling 2-qubit gate with measurements. Here we get it for free. It's just inbuilt in the tensor that we have. So, great, we thought. Now we only need local rotations, and we have a new model for measurement-based computing, but only local measurements. We got stuck a bit. So, that's surprisingly difficult. And fortunately, it's very difficult because, as Robert and Sergey have shown, well, it's just very implausible to be possible because, in fact, measurements on the state are efficiently simulerbar, and it's a good thing that we cannot find a model for computation because otherwise DQP would have been P. Okay, so fine. So can we modify the model slightly to something else? So we could take our tensors and apply a little bit of a gate that's independent of our measurements and of our algorithm, of our everything. It's just a new tensor. That's a slight modification. And the state is still a ground state of a local many-body Hamiltonian. As before, this phase, that phase, well, whatever. It's just a different state. And it's still true that 2-qubit gates are more natural than 1-qubit, single-qubit rotations. But that extra gate here allows us every once in a while to get a little bit out of the nasty plane that keeps us stuck in the Kitaev planar version of the Toric code state that makes it non-universal at hand. And the trick really is that you can't do local rotations, but you can prepare ancilla in a certain known state. And then if you do the right entangling gates on that state, it's like doing a local rotation. And then the problem is if you want to do a 2-qubit gate, then your ancilla on the way, so you have to jump over the ancilla. But all these problems can be overcome by appropriate swaps and by appropriate measurements on the way. And the most technical bit is actually to get the information in to prepare the systems in the first place. But all these problems can be overcome. And it turns out that this resource, with this little bit of an extra phase, is a universal resource for quantum computation. And it's still a ground state of a local many-body Hamiltonian, just like the state before. And we have the interesting situation that we have a kind of phase diagram, if you want, where on the one hand, we have the planar version of Kitaev's toric code state, which we know is not only not universal, but we know that it's efficiently simulerbar, as Robert has shown. Then on the other hand, we have a phase. At the other end, it's not only not efficiently simulatable, but it's even a universal resource. So we have a kind of one-dimensional knob which we can turn to go from this phase, the simulatable phase, to the universal phase. And these are all ground states of local Hamiltonians. So it's a kind of one-dimensional family of ground states being efficiently simulatable and universal. OK, I want to be nice guy with time, so I just I think I come to an end now. I skipped this. I had some teaser on the quantum expanders. If somebody's interested, you can have. Yeah. Okay. Now for something completely different. It's just an interlude. We could. It's a kind of teaser for a Blackboard discussion if somebody's interested, but Aram is not in the audience. He's the only person interested in expanders here anyway, but never mind. So expander graphs. So expander graphs are graphs in the spirit of this conference. They're highly connected graphs, and there are many ways of combinatorical and probabilistic nature of grasping what it means to be highly connected. One thing is that random walks on such graphs are very highly mixing. So just if you make a random walk on the graph, you very quickly forget where you've come from. Yeah? Specifically, if you have a d-regular graph, so d vertex will be per vertex, then A over D is the transition matrix of a random walk, And it's the point of an expander that random walks on expander graphs are extremely quickly mixing. They're exponentially quickly converging in the number of steps to the uniform distribution, which is the steady state of this random walk. So with very few steps, you're very quickly there. And that's an extremely helpful property in computer science because it can help you to get rid of a lot of randomness. For example, if you need random numbers, you want to draw a random vertex of a graph, you need like a random number over n numbers. But you can also pick an initial vertex and then do a kind of random walk on the graph. And after a number of steps, but you only need to decide where to walk on the graph, you have a kind of random number because you've forgotten where you've come from. So that's very useful in kind of getting rid of randomness, say in prime testing, where you need just very few random numbers for the same algorithm. That's very helpful in algorithm construction. I think Mike is one of the de-randomizing experts. It's a way of not de-randomizing, but getting rid of randomness. So how do you construct expanders? Well, one way is kind of the Margulis construction. So the vertex set is just an n by n lattice, n by n square. And the neighbors of this graph, of this vertex, are the images of these 4 affine transformations and their inverses. These are determinant 1 is of affine transformations, and the inverses, these are all the neighbors of the vertex, and this gives rise to a graph, and that can be shown to be an expander graph with a gap of square root of 5, 2 over 8. So it's a known result that independent of the size, you have a spectral gap of the system. So that's a construction of an expander. That's a very well-known and useful one. But how to construct quantum expanders? Well, so there's not really a notion of a quantum graph, but you could think of completely positive maps that are mixing in just the same way on quantum systems as random walks are on classical expanders. And Aram has given a very nice introduction on quantum expanders as pseudo-randomizing operations on Monday, I think. But typically it's very tricky and very technical to construct such quantum expanders, well, for good reasons. And here the only point I wanted to make, so that's the one slide, is that there's one trick such that constructing a quantum expander can be essentially for free. Namely, you need only one insight. You take this vertex set, n by n matrices, n by n, and you just interpret this vertex set as the phase space of an n-dimensional quantum system. So it's a discrete Weil system. It's a phase space, has a discrete Wigner function, as we already heard on Monday. And then, taking this seriously, you just take the same affine transformation on probability distributions. You apply it on the quantum phase space, and you're done. Yeah. So the point is, you can do a shift in phase space with Weil operators, or what are called generalized Pauli operators, and you can think of rotations in phase space by what is called a symplectic transformation. But the point really is, you do shifts and rotations in phase space, and if you take the classical expander and just do the unitary representation of all these affine transformations in phase space, then it acts on the Wigner function in just the same way as the classical expander acts on classical distributions, and you get essentially a quantum expander for free. So that's a kind of very cheap way of constructing a quantum expander just by acknowledging that you can think of actions on phase space of a quantum system in the same way as you can think of actions on such a graph. So that's the simplest known quantum expander construction that I'm aware of. Are there similar ideas for a link of graph theory or expander graphs to quantum info? I don't know, but maybe you know, right? Maybe there's something to talk about. So that's a kind of nice tool to use ideas of finite Weil systems to construct expanders. Okay, but now I really summarize. So come to the end of the talk. You can relax. Coffee is coming soon. So this talk was concerned with new models for measurement-based quantum computing beyond graph states. So for states that are very different from graph states, that can have very little entanglement per site, and they can be universal. They give kind of long-range correlations, and they can be universal. They can play around with resource states that are different from that. So the language was a kind of matrix product or tensor network approach language, which where the nice thing was that we have a mathematical object of grasping correlations where we can be very non-one-to-one of the measurements that we do in the physical systems and the correlations that inhabit the logical information that's spread out over many physical sites in the lattice. So that's a nice way of grasping correlations and relating that to the computational power of the system. But to look at a classification of quantum wires and looked at the normal form of such wires and played around with properties and what that means for like entanglement and correlation properties. And it can be seen as a kind of primitive to construct a large class of new models in a sort of quantum Lego. Oh, that's a very European thing, right? I think only European kids play with Lego, no? Yeah? Ah, but Canada is just British until, I don't know. Yeah. Anyway, so it's a kind of quantum Lego where you have your wires and you have your couplings, and it's really the limit is your imagination how to put these guys together on some graphs and think of new computational models with long-range correlations, little entanglement, or whatever properties that you would like. But we are only touching the surface. There are lots of open questions. Say, it would be really nice to classify the gapped models of ground state of nearest neighbor, say, two-dimensional Hamiltonians, which happen to be universal, where you are protected by a spectral gap in the model. That would be really nice to know, but I have, to be honest, no clue how to show this, except from some ideas where to start, but that would be a very nice property to have. Can we turn things around and learn something about the classical efficient simularity to link to Hector's question yesterday on the color code? So can we think of using that framework to talk about efficient simulatability of measurements of quantum many-body systems, and a full classification of all 2D resources would be really nice to have, which we don't have. But already the one-dimensional classification gives rise to a kind of nice picture of things. So sorry, David, I stole your picture. So you could think of, I mean, when you think of the role of these angles, so if we fix the bias parameter and think of the role of the byproduct angle, then you get a quite funny, appealing picture of what happens here, because it really shows your impact of physical measurements on what you do in your correlation system. So you can think of a large angle. So that's like the giraffe on the Bloch sphere, where the Bloch sphere is the correlation space, where the giraffe makes one movement and doof, it changes the Bloch sphere with the giraffe. I mean, it does with the Bloch sphere whatever it wants. So it's very much coupled of the physical measurement to the Bloch sphere. Yeah? But then there's this poor little bird that is on the very small angle side. So that means that your physical measurements have very little impact on your transformation on correlation space. So this little bird makes measurements and kind of walks on the Bloch sphere. Eventually, it can also turn the Bloch sphere whatever it wants. It's a universal set, but it just has to make a lot of more steps than the giraffe that just turns the Bloch sphere around. So that's kind of the questions that you can explore already in the one-dimensional classification. So I guess thanks for your attention.
Jans, yeah. I have two questions. They are both very rudimentary. One is probably grade 1, the other is kindergarten. So I share in the audience. Let's start with this one. The quantum, when you say measurement on these highly correlated systems, the way I understand measurement is from like 20 years ago, quantum decoherence, and you're bound to ruin something or change something in your system. But it looks like quite a number of this kind of measurement-based quantum computing. What kind of measurement precisely are you talking about that could preserve the full quantum coherence?
It's all, so the rules of the game are projective local measurements. So they're local, meaning the many-body system, you assume local addressability, so on-site, and it's projective. So you don't allow for generalized measurements, but local projective measurements. And they're selective. You know what comes out. So the state is pure at all times, and you do destroy coherence, of course, because if you measure, then the coherence is dead. I mean, as you're the master of. But you do know the outcome, and you will need that information. And in fact, as Dan has already mentioned yesterday, you need that information to think of computing the next step that you need to do. And that can be tricky. I mean, it's an efficient computation, but it's not only like in the one-way computer that you need a kind of parity check type thing, but sometimes you need to reroute in the lattice or do sophisticated computations in P to find out what the next step is. And what the information you need to know is the measurement outcome, and then it's pure and it's projective. So in that respect, it kills coherence, but only in the part that you have discarded anyway. The rest keeps the coherence because it's a projective measurement. So it's only partially decoherent.
It's a tricky business in some sense, right? In other words, you assume this local measurement is really local, and whatever change you can sort of compensate for it without affecting the rest of them, right? But in real physical systems, as you know, just a little bit of error or whatever sort of insufficient compensation is going to accumulate because of all these highly correlated normal coffee behavior. Is that sort of taken for granted so that we could continue on with the theoretical discussion, or is it proven sort of experimentally in some way?
No, I mean, of course. I mean, the misery starts there, right? I mean, the part of this program is, and the point of this program is to explore what freedom you have to cook up computational models. And the good news is you have lots of freedom. You can cook up new models. You can play around your flexibility in what you think what a quantum computer of that sort is. Having said that, of course, all the requirements that you say are, I mean, it's difficult to build a quantum computer. For example, a natural setting where you can think of such a computer as an optical lattice computer where you have atoms in single sides of an optical lattice. But then the addressability problem starts. I mean, Immanuel Bloch has 3 subgroups in his supergroup on local addressing. One is on electron beams, one is on using lenses, and the other one is using superlattices. But still, your requirement of having exactly one addressing site is extremely difficult. You will hit also the others a little bit. That means you screw up things that accumulates. So that on the one hand means you have to be careful about the physical implementation. On the other hand, of course, you need a fault-tolerant scheme at the end of the day. But at least this gives an avenue where to look for fault-tolerant schemes. I mean, this is all hardware.
So it's still a non-tolerance solve.
For the one-way model.
Yeah. So it's still pretty much a non-trivial issue, is that right?
Oh yeah, absolutely. But I mean, you can use the model. I mean, as Robert says, I mean, for the one-way computer, fault-tolerance is known. So I mean, that gives very strong hope that with some effort and some grad student possibly, you can show fault-tolerance also for other generalized models.
So if I just quickly add the second question, which is related to your Wigner function, when you go to the classical, okay, to the quantum expander, right? You also know, and in fact, Ramon is one of the first who pointed out the insufficiency of the Wigner function in conveying. Well, okay, I have to go back a little bit. So for a long time, people thought that the Wigner function would give you the one-particle distribution function, and that's why it's the most sort of classical state. And for a long time, people were trying to use the Wigner function to use that short circuit. But then if you really look at the Wigner function, it contains all the phase information. It could even be negative.
Yeah.
So when you do this mapping, is that considered? Or are you just using this more direct way that people are thinking that classical going to quantum is easy to use Wigner function? Well, leaving out all the.
I mean, one thing. I mean, of course, it's one-to-one. I mean, that's. I mean, the Wigner function is uniquely defined by the state, and it can be negative and will be negative in general. Even for the discrete Wigner function, they're not. I mean, that's the nice thing. There's a kind of very similar of the continuous setting and the discrete setting, that you have a kind of the parity operator and the translated phase space, and essentially the expectation value of the translated the phase operator. But the parity operator are the Wigner function in both settings, and they can and will be negative.
So, but the question is that what makes it so convenient to go from classical to quantum expander in this case? Because as you just said, it has all the quantum features in it.
Yes. Well, that's just a way of showing that you get the same spectrum in the class. It's a kind of quantum to classical mapping, in that you think of the spectrum of the expander and you get the same spectrum out. So it's a convenient way of classically looking at the quantum system. So it's a convenient tool to just use that there's nothing to show that once you've acknowledged that you can just translate in phase space as you can do in a classical system, then you are back in the quantum system.
But that's assuming something about the quantum phase information that you know also, right? Where you say this is convenient.
I'm not sure, but maybe this is some kind of semi-philosophical issue on the role of the Wigner function.
No, it's
maybe
a semi-classical approximation.
No, it's not. No. It's not. You don't assume positive Wigner function. It's any Wigner function. It's just. It's not an approximation. It's really the state. Yeah. So that's.
Okay, so it is a quantum.
It's full quantum.
Ah, thank you.
Any other questions? Yes, Robert.
I may have a question, so I have to pick one. So, I think your last slides on the first half of the talk were on generalizations of the highest code state to make it universal by modifying it a little bit. And I wonder whether you have thought about the following potential connection. So, we all know we can take a graph state, say where we have on the lattice graph where we have the qubits on the edges and on the vertices and measure the vertices in the x basis. That would give us the toric code state. And now, that's not universal resource, but if we now change the measurement angle on these vertex qubits a little bit, that gets us universal. And sort of that, now if you do this change, measure these guys on a little different basis, does that correspond to the change you have made with the tensors, or is this something different?
I mean, the honest, direct answer, I don't know whether it's exactly the same. But of course, it's of a very similar type in that, I mean, of course, the graph state in the first place that you have in the first place is a tensor network of that form that can be immediately written down. And then you make measurements, and to keep track of what comes out under that measurement, and how that's inherited by the local phase is also not a difficult enterprise, although I just don't know the answer out of my head, but it will be of such a modification. So you will get some extra guy being there on some of the wires of this tensor network. So absolutely yes, it's of that type. Whether just changing the measurement basis just gives you exactly that type of resource is, I don't know out of my head, but it's very much conceivable. But then the methods that are shown here would be applicable, certainly to the setting where you do measurement based, and that's a very interesting question. Yeah, it's good. Thanks.
Any more questions? Well, let's thank the speakers from